Hi, this is Halal. In this video, we'll talk about the increasing and decreasing functions. Also, we'll cover the concavity and convexity part of the functions. Now, a function f of x is said to be increasing at x is equal to a. A function f of x is said to be increasing at x is equal to a if in the immediate vicinity of the point a f of a. If at that point, at close to that point, if the graph of the function is rising as one moves from left to the right. If we at this particular point, if the graph of the function is rising as we move from left to the right, then I will say this is the increasing function. Similarly, if I have the function that is f of x and at a particular point a f of a, at that point if the graph of the function is falling as we move from left to the right, then I will say this is the decreasing function. Similar, here the intuition is the graph is continuously increasing and here it is decreasing continuously in this vicinity. Now this was the graphical depiction of the increasing function and decreasing function. Now mathematically it means if the value of the first derivative is greater than 0, then I will say the given function is increasing at x is equal to a. And similarly, decreasing function, if the value of the first derivative is less than 0, then I will say the given function is decreasing 1. Or I can say if the slope of the given function is greater than 0, slope means the first derivative. If the slope is greater than 0, then I will say the given function is increasing, and if the slope is less than 0, I will say the given function is decreasing 1. Now, concavity and convexity. A function f of x is concave at x is equal to a if in the small region close to the point a f of a, the graph of the function lies completely below its tangent line. If I have this function, if f of x is the function, and if I draw a tangent at x is equal to a, and if that tangent lies above the function, then this is the concave function. Similarly, if I have a function that is f of x, and if its tangent lies below, then I will say this is the convex function. So graphical depiction means if I have the graph, this means if the tangent is above the function, then it is concave. If the tangent is below, then it is a convex function. Now, the mathematical depiction is if the value of second derivative is greater than 0, then the function is said to be convex. If the value of the second derivative is greater than 0, then f of x is convex. So this is the graph of a convex function. Similarly, if the second derivative of the given function is less than 0, then I will say that the given function is concave. I will say this is the. Now we will talk about relative maximum and minimum. For functions which are differentiable at all values of x called smooth functions, one need only consider cases where f dash x is equal to 0 in looking for critical points. Now to find the critical points, we must have the first derivative equal to 0. Now, what is the meaning of relative minimum? Now we say a function has relative minimum at x is equal to a when its first derivative is equal to 0 and the second derivative is greater than 0. First derivative is equal to 0 means the slope at that point is 0. That point is 0. And the meaning of second derivative greater than 0 means the function lies above the tangent. So these are the conditions for relative minima. Similarly, the condition for relative maxima at x is equal to a is first means the first derivative must be equal to 0, means the tangent here is parallel to the x-axis, so the slope is 0. First derivative is equal to 0 and the second derivative must be less than 0. Now the second derivative is less than 0, it means that the function is completely below the tangent. So this means the relative maximum at x is equal to a. Now the implication of second derivative is used. The applications are in finding the minimum average variable cost or minimum marginal cost. We use the second derivative, or in the profit maximization or cost minimization, we take the use of the second derivatives. Okay.